Hello students. Now we are going to discuss the next numerical method to find the root of the given equation. The method is regular Falsi method. So first we discuss the geometrical meaning of the regular Falsi method. So how actually we are finding the root of the equation using regular Falsi method. So here I draw x-axis and y-axis. So here I'm going to consider a curve. So this curve is y equal to f of x. Okay, so this is the general curve I considered. So this y equal to f of x, it may be a algebraic function or it may be a transcendental. The equation of this curve is a algebraic or it may be a transcendental. So for our convenience I consider one general curve y equal to f of x. Okay, now so this curve intersect x-axis at this point. Okay, so the point of intersection of this curve with the x-axis, so this is called exact root, the value of x. So here y coordinate is 0, the value of x what we have, so this value of x is the exact root of the equation, or we can say that this value of x satisfy this given equation. So our root is here. Okay, now so by this regular Falsi method the formula we are going to derive as, so at first what we have to apply the fundamental property. So fundamental property is what? So first we take some value of x in the given function, we get the we get the value of y by taking the value of x, it say x equal to a in the given function, we get the value of y as f of a. Okay, now we take another value of x, that is b, we get the value of y as f of b. Okay, we just assume that at one value of x, the value may be negative, at other value of x, the value of the function that is y is positive. Okay, so these what is, this is called the fundamental, this is called the fundamental property. Okay, so at one value of x the value of the function must be negative, at one other value of x the value of the function must be positive. Okay, so this I'm going to take on the given curve. Suppose this is the point a, I take x as a here, and this is value of y. Okay, and then this is the point b, so the value of x is b, the value of y is f of b. Okay, so our exact root is here. Okay, now so this method is, we are finding the formula of this regular Falsi method with the help of the chord. So this, the line what I joined the points a and b, so this is called chord, chord of the equation, chord of this curve y equal to f of x. Okay, now the chord, the equation of the chord joining the points a and b is given by, I write here the equation of the chord y minus f of a divided by x minus a equal to f of b minus f of a divided by b minus a. So with the help of the points a and b, a having the coordinates a, f of a, and b having the coordinates b, f of b. So this is the equation of the chord. Okay, now what we need to do, this line, this chord intersect x-axis at this point. The point of intersection of the chord with the x-axis, so this is the value of x where y coordinate is 0, and this we say that this is our approximate root. So this is the approximate root. Okay, and this root we can denote as x1. Okay, now how we can find the root, how we can find the value of x with the help of this equation of the chord where y value is 0. At this point y coordinate is 0, so here we are using in the equation of the chord where y is 0, we get minus f of a divided by x minus a equal to f of b minus f of a divided by b minus a. Now from this we are going to write the value of x by taking the cross multiplication, and that on simplification we can write the value of x. So the value of x is given as a into f of b minus b into f of a divided by f of b minus f of a. So this is the value of x where this chord intersect x-axis. Okay, and this we can denote as a x1. So this x1 gives the first approximate root of the equation y equal to f of x. Okay, even this is also we say just general formula to find the value of x with the help of the values of a, b, f of a, and also f of b. So these values we substitute here, we get the value of x, and this x is the approximate root. But now, so our exact root is here, the exact value is here, so this is the approximate root. Now what we do, we continue the approximations, like here I take a point on the curve. Okay, so this curve I denote as c, where the value of x I denote as a x1, the value of x is x1, and here y value is f of x1, the value of y is f of x1, the point is x1 and f of x1, here is the point, right? Now what we do, again I join the points a and c. So here I drawn one more chord joining the points a and c. Okay, and this chord intersect the x-axis here, right? Now taking this new chord, and as we wrote the equation of the chord for the previous one, similarly we write the equation of the chord for this new, then taking y equal to 0, from this we get the value of x. I denote this value of x as x2. The procedure what I explained, the same we write the equation of the chord, then taking y coordinate as 0 in the formula, then we write the value of x. Okay, so that x we denote as a x2, right? So this x2 is a very simple, just we are replacing b by x1, then f of b by f of x1. Okay, So this is the second approximation, and see geometrically we can see here as this x2, this root is better approximation than x1. Okay, so this x2 is very somewhat near to exact value compared to x1. So likewise we continue the approximations, taking the another point on the curve. Again we join the points, we get the one more point of intersection with the x-axis. Again taking the equation of the chord, we get the one more value of x that we denote as a x3, so which is almost near to the exact value. Like this we continue the number of approximations like x1, x2, x3, x4. Likewise we continue, we get the better approximation. Okay, so therefore our general formula is a into f of b minus b into f of a divided by f of b minus f of a. So in the problem we are just replacing the values of a, b, f of a and f of b. Okay, substituting these values in the formula, and we continue the number of approximations. Okay, so this is the geometrical meaning of the regular Falsi method, and this is our general formula to find the value of x. Okay, now we consider the problems on the regular Falsi method. Yes, so here is the one problem. Find the root of the equation x cube minus 2x minus 5 equal to 0 by the method of false position. Okay, this method is also called as a false position. Correct to 3 decimal places. First, we consider the given function as f of x equal to x cube minus 2x minus 5. Now, the first step is to apply the fundamental property. So by fundamental property, as we explained in the previous video, we start from the 0, put x equal to 0 here. Okay, we get the value of the function as minus 5, then take next value x equal to 1, we get the value of the function as minus 6, then continue taking x equal to 2, we got minus 1, again we have a negative. See, all these three values are negative. For 0, 1, 2, we got all the negative values. Then we are putting x equal to 3, we got the positive value, that is 16. So by the fundamental property, the one value must be negative, the other value must be positive. So therefore, so our interval is 2 and 3. So we can say that the root lies between 2 and 3. Okay, do not take minus 1 and 16. The values of x we have to take. These minus 1 and 16 are the values of the function. Now we have to take the value of x, 2 and 3. Okay, now in the next so here I just explain the root we got as 2 and 3. At 2 we have a negative value, at 3 we have a positive value. It is better to write in this form. So 2 negative value, at 3 we have positive value. Okay, now the length of this interval 2 and 3, the length of the interval is 1, that is 3 minus 2, the length of the interval is 1. Now what we can do, the one trick we can apply, I'm going to reduce the length of the interval. That is, we can find the value of the function at 2.1, at 2.2, 2.3, like that we have 2.9. At x equal to 2 we have a negative value, at x equal to 3 we have a positive value. Now we are going to check the value of the function at 2.1 and we see that whether we get the negative or positive. So okay, see here at x equal to 2.1 we got a positive value, that is 0.061. So here at 2, at x equal to 2 we have minus 1 negative value, at x equal to 2.1 we have 0.061. Okay, so as by the fundamental property, at x equal to 2 negative, at x equal to 2.1 we have a positive value. See now, so 2 we have a negative, at x equal to 2.1 we have positive value. Now the length of the interval is zero point 0.1. See, the length of the interval we reduced. The reason for reducing the length of the interval is, it is, just I give one simple example. Suppose we lost some valuable thing, right? Just assume that this is our home, right? So we can search for that our valuable thing in each corner of our home. It's somewhat difficult. Then suppose if we conclude that that valuable thing is in our room, okay, we can search that thing within the room. Just see that instead of searching the thing in every corner of the home, if you search only in a single room, it is very easy. Okay, we can reduce the time. In the same way, instead of finding the root in 2 and 3, it is very easy to find between 2 and 2.1. The length is very small, so in a very easily we can find the root of the equation. Okay, so this trick you can apply in the problem, right? Only when the values of a and b are not given. If the values of a and b are given, no need to reduce. Yes, now the root lies between 2 and 2.1. So our a value is 2, b is 2.1. So f of a, that is f of 2 minus 1, f of b, that is f of 2.1 is 0.061. Now we take the first approximation x1. The formula is a f of b minus b into f of a divided by f of b minus f of a. We substitute all the values in the formula, and that on simplification 2.0942. So this 2.0942 is between 2 and 2.1. Okay, the next work is see that, so 2 and 2.1, we got the new value between 2 and 2.1, which is 2.09, 2.0942, 2.0942. Yes, now what we need to do, this value of x we substitute in the given function. Okay, just this is our x1. We substitute this value of x in the given function, and we see that whether we get negative or positive. See, substituting this value in the function, the value is minus 0.0039. Okay, so which is a negative. So negative means now we have to decide the new values of a and b. The new values of a and b, how we can decide? At x1 we got the negative. I suggest while solving the problem, you better draw line like this, so that we can easily choose which is a and which is b. So now we have a negative value at a 2.0942. You can write here, this is a negative value. So at this point we got the negative value of the function, and at 2.1 we have a positive. So therefore our new values of a is 2.0942, and this is our b. We cannot take this and this point, 2 and 2.09 we cannot take, because both are negative. The one value must be negative, the other value must be positive. Therefore our new value of a is 2.0942 and b remains same, 2.1. So taking this a 2.0942, b as 2.1, we continue the next iteration, and you have to write clearly. So our new value of a is 2.0942 and b is 2.1, and write f of a and f of b values, and denote the second approximation as a x2. Okay, and substitute similarly a similarly apply this formula, and substituting the values we got 2.0946. Okay, Now this 2.0946 and the first approximation 2.0942. So the question is finding the root correct to three decimal places. Correct to three decimal places means comparing this x1 and x2, 2.094, 2.094, and here also 2.094 up to three decimal places, these are same. Now we can stop the iteration. Correct to four decimal places, see 2.094 to fourth decimal, 2.0946. So these are not correct to four decimal places, correct to three decimal places, right? So this is the, so therefore, so our final answer is 2.094 up, correct to three decimal places. Okay, and finally you can write our approximate root is 2.094. So similarly you can try some other problems. So see, even in the second here also, the root lies between 2 and 3, the one value negative, one value positive. In this problem also we reduced length of the interval 2.7 and 2.8. At 2.7, see 2 and 3 is the interval, and we check for the values of values of the function at 2.1, 2.2, 2.3, 2.4, 2.5, like that continuing. At 2.7 we have a negative, at 2.8 we have a positive value. So therefore our interval is 2.7 and 2.8. Now taking a, b, f of a and f of b, and our first approximation is x1. Applying the formula, we got 2.7404, which lies between 2.7 and 2.8. Similarly, as I explained in the previous problem, you check the value of the function at this new value of x, we got negative. Okay, so I suggest you better draw the line. Okay, if you draw the line, it will be very clear. That is 2.7 and 2.8. This is our interval. At 2.7 we have a negative, at 2.8 we have a positive, then we got the value, that is 2.7404. At this value we have a negative, so you better write at this, above this value as a negative. Now see, if you draw this line, it is very clear, it is very easy to take the values of a and b. See, the one value must be negative, the other value must be positive. We cannot take these two as a and b. Now the value our a is this and b is this, negative and positive. Taking again new values of a and same b is 2.8 again, then f of a and f of b, then we find the second approximation x2. Like that we continue, and we got the second approximate root as 2.7406. Similarly, we apply the procedure, we find the third approximation x3, 2.7406. So this 2.7406 x, and comparing with the x2, both are correct to four decimal places. Okay, so like this we can continue some other problems. And so last one point, here in this problem, uh, the function is here, and the values of a and b are given, a equal to 4 and b equal to 5. Okay, so at a equal to 4 the value of the function is negative, at b equal to 5 the value of the function is positive. Okay, see in this case, do not reduce the length of the interval. When the values of a and b are given in the problem itself, no need to reduce length of the interval. This point you remember. If the values of a and b are not given, then you can decide whether we have to reduce or not. Okay, even though without reducing the interval, we can find the roots of the equation. It is only the difference is number of approximations. If you reduce length of the interval, the number of approximations will be reduced. Okay, so here a equal to 4 and b equal to 5, keeping this only, you have to continue. And it is given that in 3 steps, means up to we have to find x1, x2 x3, x1 is the first step, x2 is the second step, and x3 is the third step. Okay, so like that we have to continue. Okay, okay, thank you.